This is a domain per domain review of CISSP, and today we are at the fourth session, and this is CISSP Domain 4 review. I'm Chandresh Singh. I'm CISSP certified professional. I've been working with the PSP for more than 8 years now in the infosecurity domain. You can look me up on LinkedIn at XSNChan. Something about the InfoSec train. It was established in 2016. It is a reputed training institute which have more than 70 trainers which are highly skilled, and we have trained 15,000 plus people so far, and we have more than 100 corporate deliveries so far, and that is our credentials. So that's it. We have certain corporate clientele, which includes Deloitte, Microsoft, Samsung, Infosys, etc. And we are global learning partners with Microsoft, CompTIA, ISACA, etc. Coming to the questions from the last session. So the format is like, we discuss the questions from the last sessions that we have. So we have domain 1 review, 2 review, and 3 review. So the questions here will be from those 3 domains. And I'll read out the question for you. I'll read out your options for you. Then I'll give you 10 seconds for you to drop your answers in the chat box. And once your 10 seconds are over, we'll discuss the questions. We'll discuss how to answer the question properly. So the first question is, Tom is responsible for maintaining the security of systems used to control industrial processes located within a power plant. What term is used to describe these systems? So yeah, 10 seconds are up, and most of you have gotten it right. It is SCADA only. We discussed SCADA in last session in our systems architecture, where we discussed industrial systems. That is where we discussed about SCADA. Moving on to the second question. Chris wants to verify that a software package that he downloaded matches the original version. What hashing tool should he use if he believes that technically sophisticated attackers may have replaced the software package with a version containing a backdoor? Your options are MD5, 3DES, SHA-1, or SHA-256. Your time starts now. And the time's up. So yeah, there's a divide in chat section. People are either opting A or D. So let's discuss this question. First of all, we'll go with elimination. 3DES is a symmetric algorithm. It is not a hashing algorithm. So this is clearly not the option, not the correct option. Then we come to MD5. MD5 is MD5, SHA-1, and SHA-256. All three are hashing algorithms, but MD5 is known to be can be exploited. MD5 is already known to be exploited, and SHA-1 is also vulnerable already. So the correct option is SHA-256, which is the correct option, which is secure as of now, which is a secure hashing algorithm as of now. Moving on to the third question. Alice and Bob would like to use an asymmetric crypto system to communicate with each other. They are located in different parts of the country, but have exchanged cryptographic encryption keys by using digital certificates signed by a mutually trusted certification authority. So we discussed about digital certificates and trusted CA in the last session. The questions are, if Alice wants to send Bob a message that is encrypted for conditionality, what key does she use to encrypt the message? Your options are Alice's public key, Alice's private key, Bob's public key, or Bob's private key. The time starts now. Yeah, time's up. So again, there is a divide in the chat. So let's discuss this question. So Alice wants to send Bob a message that is encrypted for confidentiality. So if I wish to keep it confidential, I want only Bob to be able to read the message. So I'll encrypt it with Bob's public key because Bob is already having the private key uh, of the public private key pair. So if I encrypt it with Bob's public key, only Bob's private key will be able to unlock it, be able to decrypt it. And that is why, to protect confidentiality of the message, I'll encrypt the message with Bob's public key, since Bob is the recipient and he is already having his private key. The second question is, when Bob receives the encrypted message from Alice, what key does he use to decrypt the message plain text context? Your options are Alice's public key, Alice's private key, Bob's public key, and Bob's private key. Your time starts now. Okay, guys, time's up. And all of you have gotten it right. So we'll skip any discussion around it. If you wish, if you want me to discuss it, pin it, we'll discuss it by the end of the session. Moving on to the recapping of previous sessions. So far we have 3 sessions around CISSP domains, and all 3 sessions were focusing on individual domains. So domain 1, 2, and 3 we have already reviewed. We talked about, in the beginning, we talked about how CISSP is structured. You have 8 domains, you have 100 to 150 questions, you have 3 hours to do it. And there is one key takeaway here is, if you manage to solve these first 100 questions and score more than 70% in that first 100 questions, you'll pass CISSP test without needing to solve any further questions. So I did it in some 110 minutes, and it is possible. So yeah, so that is how CISSP is laid out. If you manage to solve 100 plus questions with scoring 70% plus marks, and since it's a cat, so the questions do adapt. You start with easy questions, and the difficulty increases with time. So it is possible to finish the test before the allotted 3 hours. So that is how it is. Then in security, we focus on CIA triad, which is confidentiality, integrity, and availability. We have already discussed it. I won't discuss it here again. If you want me to discuss it again, you pin it. We'll discuss it later on. We talked about frameworks, risk management framework, risk assessment and analysis. We discussed how both the two are related. Then we came to people, the canon of ethics of CISSP by IC square. Then who can raise a complaint against breach of certain canons? There are 4 canons and stuff like that. We discussed about it. Then we talked about a risk treatment plan, which derives from your risk assessment and analysis, entire risk management framework. It is a part of that. And then we talked about residual risk, which is nothing but whatever risk you have identified minus the controls that you have put, then whatever risk is left over, that is your residual risk. Then we talked about the type of documents that are there. Policy, procedures, baselines, and guidelines. Policy is overarching document, then procedures are step-by-step guides, and baselines are your point-in-time configuration, and guidelines are good to have documents. Good to have recommendations, basically. Then we talked about asset inventory, we talked about data classification. In asset inventory, we talked about the entire life cycle. Similarly, in data classification, we talked about life cycle, we talked about categorization, we talked about labeling and marking. Label and marking, basically, the distinction was in marking, you also mentioned the media handling requirements. And in labeling, you just mentioned the classification. Then we talked about the kind of roles that are there, like data owner, data steward, and all. So we talked about that. Then there is data lifecycle. I've already talked about that. Then handling of data. We talked about how we shall restrict the amount of data that we capture at the source, because at the end of it, it becomes a liability on the company who is collecting the data. So that is one key takeaway from data handling. Then archiving basically is long-term storage of data which is not being actively used. So that goes to your archiving. Then we talked about defensible destruction of data. Like whenever you are done with the data, you shall destruct it in a way that you can defend in a court of law. Then there is data protection. Then we talked about privacy also over there. Then we came to system architectures and security models. In system architectures, we talked about the client server model. We talked about virtualizations. We talked about cloud, how cloud can be delivered, like function as a service, infrastructure as a service, platform as a service, or software as a service. Primarily, there are 3 only. But nowadays there is function as a service. For example, AWS Lambda is a function as a service. So these offerings are also coming into picture nowadays. There is IAC also, infrastructure as a code, which is also an important term to remember when it comes to cloud. Then going to security models, we talked about how Clark-Wilson is made. There is unconstrained CDIs and DI. Okay, constrained and unconstrained data, and when the user is interacting with constrained data, it comes through a transformation set of rules so that no unauthorized changes are done in your data. So it is basically focuses on integrity. Then again, Biba also focuses on integrity. Then we talked about Bell LaPadula. So Clark-Wilson, the key distinction between Clark-Wilson and Bell LaPadula and Biba is Bell LaPadula and Biba are lattice-based models, and Clark-Wilson is not lattice-based. Bell LaPadula focuses on confidentiality. That is what you need to remember about it. Then we came to common criteria of assessment. Then we went to TCB, that is trusted computing base. Then we went to reference monitor concept. Reference monitor, we talked about how the security kernel is built and whatnot. So that is what we have already discussed. Then we talked about cryptography in the last session, in which we talked about symmetric, asymmetric encryption, and we discussed briefly about PKI, the public key infrastructure. And we have had a healthy discussion around that. So if you guys remember, we discussed about digital certificates, we discussed about digital signature. I showed you a few example of how PKI actually functions in the real world. I've shown you the browser where all the trusted root CAs are stored. Link of previous session. Kapil, if you're still there, can you please drop the link of YouTube link? Go on YouTube and look for InfoSec Train. So you'll find it over there. Okay, now again, resuming to the questions from this is the last one from the previous session. Last time around, we have had just too many questions and we ran out of time. So I cut short the number of questions that we are going to solve every time. Maybe in the longer sessions, in the full sessions, we may be able to do more questions, but not in the express sessions because we run out of time very quickly. So yeah, coming to the fifth question, which is Health Tracking App Inc., HTA, is a US-based corporation that develops and sells apps that its customers can use to track various aspects of their own health. Basically a health tracking application, from their daily exercise regime to various medical test results and comparative statistics over time. HTA's customer data is breached via vulnerability in its application programming interface, that is API. This vulnerability is discovered to be a result of a recently announced security flaw in the underlying Java framework that HTA uses for the development of its app. Which of the following best describes the root of this problem? Option A is HTA failed to manage the risk associated with its supply chain. B, HTA failed to apply the critical patch in a timely manner. C, HTA stored critical sensitive data in a cloud. And D is HTA chose a risky language and framework for its development. Your time starts now. Okay, time's up. So everybody except for Jashri has unanimously answered option A. Let's talk about it a little. So, okay, recently announced security flaw. They did not mention here that there is a patch which is already out. So B is already eliminated, Jashi. B is not a right answer. They didn't talk about how they are storing the data on cloud. So that is also eliminated. And a risky language and framework, there's no proof of that also. So by elimination, your option A is correct. B and C and D are not in the context of this question. Now coming to the domain 4, which is communication and network security, we'll talk briefly about the fundamentals of it, because again, it's an express session, and I learned from the last session that if we go in details of anything, we quickly run out of time. So let's stick to the basics this time around. So in communication and network security, what is the most important thing is that you need to remember is you need to understand is OSI model. And I'll focus mainly on this, on making you guys understand how OSI model functions. And that is mostly the discussion, that is mostly what this discussion will revolve around. So OSI is basically a reference model. It is no guideline, nothing. It is a reference model. Just for what is a reference model? A reference model is for, so if I do not have, if I do not know where I want to go, I will never be able to get the right tickets for the right destination because I'm not sure about my destination. And how do you understand? How do you know about the destination? You know about the destination by a path. From where do you buy the tickets? You buy it from a ticket counter or maybe from a travel agency and whatnot. So these are the when it comes to traveling, these are the things. These are the moving parts that are there in question. Buying the ticket, planning your route, planning your journey, planning your luggage, and on. Similarly, when it comes to network communication, in order to allow all the manufacturers, all the vendors to have a framework to form their protocols, form their devices, form their logic and whatnot, whatever moving parts that are there in network, in order to give a framework to all the manufacturers, this OSI model is in picture. So what OSI model, it's a 7-layer reference model. I'll give you a semantic to understand this. So let's put down the numbers first. So you're first starting with the first layer. This is your physical layer. Then there is your data link layer. Then there is network layer. Then there's transport layer. Then there is session layer, and there is presentation and application. Now there are two important things to understand about this. There can be different devices, different protocols, which may be running on these different layers. So how do they talk to each other? There's a interlayer communication only. Like one layer understands the language of the other layers. So for example, I have some device which is operating on layer 3. So any device which is operating on layer 3 will be able to understand the language this device is speaking. Whatever device is operating in one layer, all the other devices which are operating on the same layer will be able to understand the language that is speaking. That is what we call the protocols. The language is the protocols. Now, the second thing is when we go down the stack, encapsulation happens. What is encapsulation? Say on application layer, you are having one HTTP server or one HTTP client running. Now you'll create some request here in user understandable language, but that is not something that the machine understands. Machine understands binary. And when it comes to physical medium, you either have copper, say metal, or you have optical medium, or you have air as a medium. So your physical or metal medium is generally your twisted pair, your UTP cables, that is Cat 1, 2, 3, 4, 5, 6, 7, 8, and whatnot, 6 and 5e, that is up to that. Then your coaxial cables that you use in DTH and all. So you must have seen coaxial cable there in your DTH, your set-top box to your dish antenna, that the cable that runs between the two is your coaxial cable. Similarly, in case of VSAT, we use coaxial cable. In general, day-to-day networking, we use UTP, unshielded twisted pair. So that is your metal medium. Second is optical medium. What is optical medium? Your optical fiber. So here the data transfer happens based on the photons, movement of photons. Here the data transfer happens based on the movement of electrons in the physical medium. Then you have wireless. So basically air becomes your medium and microwaves do carry your messages or data or payload across. So since here the user is generating something, the content on user legible language, and the data ultimately is traveling on in terms of bits and bytes, basically bits here. In case of electrons, it will be one single electron maybe. In case of photons, it will be a state change. Say light up is 1, light down is 0. So it is a pair of bits that we are transmitting. So when you encapsulate, you basically break it down and convert it to the language that machine understands. Application generates user readable content, and it's the encapsulation which happens afterwards, which converts the original message or original data, whatever we were transmitting, we are trying to transmit across the network, to the bits that are actually going to travel in the media. Okay, so in application, your top level protocols are running like HTTP, FTP, DNS, stuff like that. It is all those protocols, all those high level protocols, application protocols are running here. Then what your presentation does is, your presentation layer encodes the this message in a standard character set. Say your network is using Unicode or it is using ASCII characters. So that is what presentation layer does. It standardizes whatever message that you have received from the upper layer, the application layer, and converts it into a standard language that that the network understands. So either Unicode or ASCII or whatever character set that is being used, it will convert or standardize the message that you are inputting. Now comes your session layer. Session layer basically maintains the session data. These last 4 layers are very important. Here is your transport layer. Transport layer is responsible for ensuring that your data is went across end to end. So this is where your TCP and UDP protocols operate. This is your transfer control protocol, and this is your user datagram protocol. So, and this is a stateful, a connectionful protocol. This is connectionless protocol. What does that mean? TCP ensures that your data is received there, and then it has received an acknowledgement that, yeah, I've received the data, and it is all right for you to close the session now. But in case of UDP, UDP blindly throws the data at the recipient's end, and it does not check whether the data has received on the other end or not. There's no error correction, there's no error checking, and there's no collision prevention or detection. It just simply is a sessionless protocol, and it does not care whether it cannot give you an acknowledgement to as to whether your data is received on the other side or not. And TCP does the opposite. It creates a session between the two. It ensures that the data is received. If the data is not received, it will ask the source to resend it or something like that. So there are coping mechanisms built into TCP. Then comes your network layer. Network layer is where your IP works. Internet protocol works on network layer, and certain devices which also operate on network layer are your router, your packet filtering firewall. So these are the devices which run on your network layer. Similarly, some of the protocols which run on network layer are ICMP, Internet Control Message Protocol, which is used to test whether the functionality of the devices. For example, your traceroute functions on this. Sorry, traceroute nahi. Your ping functions on this. Ping is a simple utility which is used to check whether an IP address is available on the network or not. For example, I have I'm going to ping google.com. So it gives me the IP address, and it tells me the round trip latency. It took 2 milliseconds for it to go to one packet of 32 bytes to go to Google servers, this particular server of which IP address is mentioned here, and return to my PC in these 2 seconds. The average time is 2 seconds, and there's 0% loss, and all 4 packets that were sent were received also. So this is ping, which runs on ICMP, which functions on your layer 3. Then we come to data link layer, where there is MAC, your media access control protocol, and LLC protocol, which operate here. So MAC, what is MAC? MAC is basically your physical address, which is unique to your device. So most of the internet functions on this IP address, MAC address, maybe FQDN also, and that's it. And your ports. Ports are like portals. So most of the internet functions on this IP and port combination, and then your L2 communication, whatever happens on layer 2, happens based on the MAC address table, which is basically a mapping of IP address and MAC address. So whatever MAC address MAC address table is a mapping of MAC address to your port number. So in say an L2 switch, if you have a device connected on port 1, then there is port 2, then there is port 3, and so on. So typically a switch has 24 ports. A manageable switch, basic manageable switch has 24 ports. What a MAC table does is a MAC table maintains a list of the MAC addresses which are discovered on certain ports. So for example, in port 1, say you have discovered a MAC, the switch will maintain a binding that on port 1 I have this MAC address. Then you have something called ARP, address resolution protocol, which maintains a list of IP address to MAC address. So for example, if I want to show you ARP on my Windows machine, if I run ARP A, I'll get all the devices which are all the devices which are there in my local network, their IP address and their physical address. I'll get it here. So that is what ARP looks like. It is basically a table, a mapping of IP address to their MAC addresses. And then there is another table called MAC table, which maintains a list of MAC address to the corresponding switch port on which that particular MAC address is discovered. Okay. Now getting back to the 7-layer protocol. So now that you have already understood, or now that you're already knowing the name of the 7 layers, I'm not going to mention the name of the layers now. I'll always use the term L1, L2, L3, and so on and so forth, L7. Okay? Is it okay with everybody? So I'll be referring to, instead of saying data link layer or physical layer, say physical layer, I'll say L1, data link, I'll say L2, network link, in network layer, I'll say L3. Okay. So we were talking about encapsulation and how encapsulation happens. When we are coming down, encapsulation happens. When we are going up, decapsulation happens. And that is to standardize the language that the devices speak, so that the layer compatibility, intra-layer communication is happening. So layer 3 devices can understand layer 3, the language that layer 3 devices speak, because the data is structured in a certain manner, which is called a packet. So whatever piece of data which resides on layer 3 is called a packet. Whatever sits here is called a frame, layer 2. And then comes your physical medium, online, data online, that is basically bits, pulses of electricity, or photons in case of optical medium, depending on the media that we are using. So what is encapsulation? Which generally happens somewhere here. So encapsulation basically is transforming or adding the header and trailer to your message. So anything which traverses on a network generally can be any unit of data which is traversing in the network can be broken down to two parts. One is your payload and other is your header information, and sometimes a trailer, but generally it is a header only. Okay. So payload, what payload is? Payload is basically whatever your L6 has given. So L6 is your presentation layer. Presentation layer has normalized the message data, and that becomes your payload. What will be the header information? Header information will depend on the layer that we are talking about. So for example, in case of L3, in L3, there'll be your source address, your destination address, and stuff like that, and whatever port you're going to, and stuff like that. And if it is TCP, there'll be more header information. When it comes to layer L4, there'll be, depending upon the TCP or UDP, the size of the header will change. So TCP has a larger header because it is a session-based protocol and it requires more information in order to create a session and basically do the handshake. I think last time around we didn't talk about TCP handshake also. So TCP handshake basically looks like this. There'll be a SYN packet sent to the destination. The destination will acknowledge the SYN which it has received from the source and send its SYN. And then finally, the source will acknowledge the SYN which the destination had sent. So this acknowledgement is for this SYN, and this acknowledgement is for this SYN. And here is your sender, here is your recipient. Okay. Sorry guys, my pen is not working properly today, so I'll have to constantly keep on erasing entire thing. It is frustrating. I was trying to fix it beforehand, but I'm really sorry for this. Okay, so encapsulation, decapsulation, we have already understood. We have understood packet, frame. And now let's talk about the typical devices that you will see in each layer. So typical devices and protocols that we'll see in each layer. Layer 1, the devices or the protocol that you'll be dealing with is generally they can be a repeater. So repeaters are nothing but say you're sending a electrical signal across the wire. After some the material through which you're sending, the medium through which you're sending the message or the electrical signal will have some resistance to it. Okay, so the signal will get attenuated. What is attenuation? Deterioration of quality of the signal over the time, over the length of this medium is what we call attenuation. So quality of your signal deteriorates because there is resistance in the material on which your message is going or the signal is traversing. So what a repeater does is, repeater takes the same input, amplifies the signal and forwards it without changing anything. So layer 1 devices are very simple devices. There'll be no logic which is involved. So these devices are super fast. Okay. Then comes your layer 2 devices. Layer 2 devices that you typically see is a switch. The symbol of a switch in a network diagram is this. So whenever we talk about switch and you see this diagram, this is a switch, layer 2 switches. There is also possible nowadays, there are L3 switches also which have routing capabilities built in. But what you typically see when we talk about switch, it is generally L2 switch unless explicitly told that it is a L3 switch. Okay. And what I've told you about switches, switch maintains a MAC address table. What is that is your mapping of MAC to the specific port. So say you have connected a computer on port 1 of the switch and the computer is having MAC address MAC 1. So MAC table will look something like this, that MAC 1 is available at port 1. So every time there is a request for a certain MAC, the switch will know that which port this frame shall go to. Okay. So say some packet has arrived with some frame has arrived with destination address as MAC 1. The switch will simply forward it to first port instead of broadcasting it to entire channel, hence reducing the chances of flooding the entire channel or collision. Okay, what collision is? Collision, when we talk about topologies, we'll talk about collision also. So collision basically, let me figure it out here. Let me tell you about collision here only. So collision basically, say it's a bus topology. We'll talk about it when we talk about topologies, or let's talk about topology itself. So topologies, what is topology? Topology is nothing but how your devices in a network are arranged. So they can be bus, tree, star, mesh, ring. Okay. What is ring topology? Let's start with the most basic and most archaic one. This is how a ring topology looks like. It is called a token ring topology because a token is passed throughout this ring. And whoever says that, okay, say this computer, these are different computers. This is computer 1, this is computer 2, this is computer 3, this is computer 4, and a token is passed. And as soon as one computer, the computer 2 says that, okay, I want to send some data to computer C, it cannot send it like this. It will have to traverse through this, and this. So you can clearly see that what is the problem with this topology. Say if a cable is cut here, even if my this cable is connected, the data won't be able to reach here, or because it cannot go from here to here. So this is what ring topology looks like. Then comes your mesh topology. Mesh topology, we can say, is the most expensive one because it uses the most amount of cable. So every node in the network will be connected to every other node in the network in case of a mesh topology. So this computer will be connected to this. This computer will also be connected to this and this. Similarly, this connection, the computer will be connected to this. This is how mesh looks like. So it is highly redundant. You have many data paths to choose from, but it is very expensive to set up. That is why we do not see much of mesh topology nowadays. Then we come to the star topology. What star topology looks like is, we talked about a switch. Switch is an L2 device. So one switch and multiple computers are connected to this switch, and this switch decides where will the data go and how will the data flow based on the MAC table which is there, which is nothing but a mapping of MAC address to the port of switch. So in whatever port, it discovers the MAC address, and if the destination address matches the MAC address to that port, it forwards the packet to the forwards the frame to that port, so that it reaches the destination. So this is how a star topology network looks like. Most advanced LANs to function on star topology itself. And then it is your bus. In bus, you have a single cable with which all the computers are connected. So you can see what the problem here is. If say I want to send data from here to here, and this also wants to send data from here to here at the same time, or here to here at the same time, there's a collision point here. The data won't be able to, so say if I send the data at the same time from here and here, the data will collide here and nobody will receive the data. That is what collision is basically. When two devices on a network send the data at the same time and the network is overwhelmed, your media is overwhelmed, and hence cannot okay. And hence data cannot reach that specified destination. That is what bus topology, that is how bus topology looks like, and that is what collision looks like. If the data is unable to reach the destination. What is tree topology? Tree topology is basically an extension of bus topology. So you have this bus, then you have another bus in which you have another set of computers which are connected. So if say this computer wants to communicate to this one, it won't have to go till here, then come back here. It can simply come here. So that is how tree topology looks like. It basically divides the collision zone. So this is one collision zone, this is another collision zone. So this is what it does in tree topology. This is how the network looks like. When it comes to collision, we also have concepts of CSMA, CD, and CA. What is that? Carrier sends multiple access. This is a technique of pushing data simultaneously, and this operates on L1, layer 1, that is physical layer. What is collision detection? What is CD? CD is collision detection, and CA is avoidance. Avoidance is what? If there is a collision in the network, it won't send data at all. If this is what we use in wireless media. So in wireless, if somebody is sending data, or if there is a chance of collision, nobody sends data on the channel. In case of collision detection, it can detect the collision and then either can change the path or can choose not to send data. So that is your carrier sense multiple access, collision detection and avoidance. Okay. Hope you're with me so far. So we have talked about the typical devices per layer. We have talked about typical protocols per layer and what to expect from different protocols. Let's move on to WAN, which is wide area network. So so far, and what is wide area network? Wide area network is basically when you're talking about multiple geolocations, communicating across multiple geolocations, and the most important technology or protocol in WAN is MPLS. MPLS is nothing but your multiple protocol label switching. So what happens is, why we talked about encapsulation is, and that is something we'll also need in case of tunneling. So tunneling is something, let's talk about MPLS and tunneling simultaneously, because I think I'll be better able to make you guys understand it in a single, in terms of a single concept. So we talked about the payload and header information. Okay, you have header and payload in whatever unit of data is traversing your network. So what tunneling does is, say you have underlying infrastructure which uses a different protocol than what you're using. Say you're using IP network, and you're using IP network, and the devices on the either end, the L3 or L3 devices on the either end do understand IP network, but the one in the middle do not understand it. Say there is ATM running here, asynchronous transfer mode, that is running here. This is a separate transport. This is a separate protocol which is running here. But your IP devices are not aware of this. So what we do is we do tunneling. We simply do what tunneling basically means is your encapsulation has happened from layer 7 to 1, and your data is ready to now go on wire. But before that, we encapsulate it. So this is your header and package, header and payload. This is your header, this is your payload, and then you encapsulate it again. So you add another header to it, and that is what your tunneling looks like. Basically, this header information will only be readable to this. The devices at the middle will be needing just this header information in order to make the data reach from this source to this destination. That is how we tunnel something. Now, the one thing which is lacking in tunneling is your data is not secured. You have added a header information, you have encapsulated your data, but you have not encrypted it so far. So that is where your VPN concept of virtual private network comes in. And that is where we talk about IPsec tunnels. And that is where we talk about TLS, SSL, and say SSH. So these protocols comes into picture in case when you want to encrypt your data in the tunnel. And unencrypted tunnel is GRE, your generic routing encapsulation is the protocol which is used to form such unencrypted tunnels, which basically adds a header information on top of the packet which you have already framed. Your packet already contains a header and a payload. Payload is your actual message, header is your actual header information, and then the tunneling protocol adds its own header, so that even if your end-to-end devices does not understand the protocols used in the middle, in between the network, in between the two L3 devices, they'll be still able to communicate on the same language that they understand. That is their IP network stack. So if these are operating on IP network and this is operating on something else, then you can simply form a tunnel, say GRE tunnel, which is unencrypted tunnel, which only adds a header information. And your entire payload contains your header, actual header and payload. So this header and payload, the actual header and payload is visible here only. The actual source and destination is visible here only. And the information of this destination is visible here. So this header contains the destination of the destination address of this side, not this side. This side, only this header will come. So after decapsulation, you lose this GRE wala header on this side. Okay, so that is how tunneling works. Now coming to MPLS, what MPLS does is, as the name suggests, it adds a label. So MPLS are very fast switched networks. So as soon, say this is your ISP, Internet Service Provider, who is your MPLS provider also. This is working on MPLS. This is your edge router, and this is your another edge router. You push it in MPLS, MPLS will simply add a label to it. And instead of, again, like header, instead of looking into the payloads header, it will simply check the label and fast forward it to this edge router, so that there is, again, it is useful when there is multitude of technologies involved in between the two networks. This kind of a technology is used so that the devices which understand a different language may communicate with each other. So these are using IP network, and this may not be using IP network. So that is where you use such kind of a technology of tunneling or MPLS. Now coming to converged protocols is again something similar. So this is what we call FCoE. FCoE is fiber channel over Ethernet. So basically imitating optical fiber channel like communication protocol stack over your Ethernet. Ethernet is your electronic medium, that UTP that we are talking about, the copper cable that we were talking about is what your Ethernet is. So fiber channel over Ethernet is a converged protocol. Again, when your underlying protocol, underlying network stack doesn't understand the protocol that you're talking in, that the two devices are talking in, you use converged protocol. Then coming to wireless, we have Wi-Fi, which is governed by IEEE's 802.1x standard, 802.111 standard. Then you have WiMAX, which is basically a wireless communication protocol, which is defined under 802.16, IEEE 802.16 standard. And WiMAX is generally for longer distance communication, say up to 90 to 100 kilometers. Then you have your cellular communication, GSM CDMA. GSM CDMA, you must be knowing that there is why this is called cellular connection, because you have cell towers located at the center of this cell, and which provides coverage within the cell. So there is inter-cell handovers and whatnot. So this is how your cellular network operates. There's a cell tower in the middle, which ensures communication between different cell towers. And whenever your device moves from one cell to another, there's a handover happens from one cell tower to another. So that is how it operates. In wireless, we have so if you are using, you must be aware with a Wi-Fi router, and if you're using Wi-Fi routers, you must be aware with WPA and WPA2 most certainly, because in wireless you have something called SSID, and then you enter your password. So SSID is your network name basically. If I want to show you, I can show you the SSID of my network, which is, just give me a second. This is my Wi-Fi. Okay, so this is what an SSID looks like, and this is stating secured. How it is secured? It is secured with a password. So that is where we use WPA or WEP or WPA 1.2. WEP is compromised. It is insecure. It is no more in use. WPA is also not in use anymore. WPA 2 is the present standard that we use nowadays. Coming to the IP address is like your home address, your street address. So it is nothing but a four segment address. Let me just, yeah. IP address is a 4-segment address which is divided by dots. So this representation is called dot decimal representation. Okay, it is a 32-bit address that is something you need to remember. Similarly, the next iteration of IP address is IPv6, which is a 8-segment address, and it is a 128-bit hex address, generally notated as XX:XX:XX. So it is called a colon hex representation. Now, when it comes to IP, we can talk about subnetting and whatnot. Yeah, we can talk about subnetting. But before that, okay, let's talk about subnetting only. Say, and in IP, you have in IPv4, you have different classes of IP network, say A to E, which are used for different purposes. Some are public, some are private. This is an example of a private IP address. Just give me a second. Okay, so your 10.10. Just a second. So this is an example of an IP address, for example, 10.0.2.1, and this is a private IP range. Similarly, I can show you my IP address. So this is 192.168.119. This is again from private IP itself. So how come I'm accessing internet and still having a private IP address? Because if you wish to communicate on the internet, then you'll have to use your public IP address. So what happens is, here is your private IP address, here's your public IP address. What happens is, your ISP has a pool of public IP addresses, and public IP addresses are very costly and less in number. So generally, nobody has a static public IP address associated with them. What happens is the home router that you must be having, which is having a WAN connection, or maybe having a Wi-Fi antenna also. When you connect to this, it creates a local network of its own, and that assigns you an IP address. So when it comes to yeah, just give me a second. Let me show you that command prompt screen again and IP config. So this is the IP address, my home router. This is my gateway 254, and this is my current IP address, and this is all private IP. So what your router does is your router acts as a gateway for all the computers or mobile devices which are connected in your home network, and then there is a single WAN connection which goes to your ISP, and only when the ISP, only when the packet needs to go out, say to Google servers, then then the public IP of the ISP will be used to communicate with the public IP of the Google, public IP of Google. Now there's one thing which comes into picture, which is called NAT, which is network address translation. So what happens is, in case of IPv4, since there's a crunch of IP addresses available, there is a limited number of IP addresses available since it is just of 32-bit in length. So we use NAT, which is called network address translation. What it does is it takes a connection on a public IP address and translates it to a private IP address, and vice versa. So when incoming connection is there from public to private, there'll be a public IP address, say 59.163.35 or something. Similarly, it is mapped to a private IP address and say 10.02.56 or something. Okay. So whenever a request from public lands on this IP address, NAT will translate it to this IP address and the communication will happen. And when the return traffic goes, it will take it will again be natted to 59.163.35, whatever IP address that we have identified over there. So that is what the concept of natting is. Now coming to subnetting. Subnetting basically comes to classless routing. What classless routing is basically is, so we have talked about the 10.02. Say this is what my network is like. This is what my IP address is. Now what is this /24? Let's go back to this screen. So here you'll see that there is one IP address, then there is one subnet mask, and then there is one gateway. So there are three important things. What a gateway does is, a gateway basically is the medium between two networks. It connects two networks. Okay. So gateway generally is a L3 device. It may be a router or an L3 switch. Okay. What gateway does is, whenever your traffic needs to go out from this network to another network, it will land on this IP address. It will take this gateway IP address. It will address to that gateway IP address. And if it wishes to talk within this network, then there'll be your MAC table coming into picture and ARP coming into picture. So ARP will translate IP to MAC, and MAC will translate IP to port, and that is how you communicate within your network. And when you wish to go out of your network, then you go through gateway. What your subnet mask is? Subnet mask basically tells us about the network and host bits in your IP address. Network bits, host bits. When I say /24, so you have 32 bits. You have 4 segments, each of 8 bits. When I say /24, that means 8, 8, 8. That is 24 bits are fixed and are network bits. And these remaining 8 bits are your host bits. That is the concept of subnetting. So why we do subnetting? We do subnetting. I've told you about the topology in tree. We do it for dividing the collision zones. So every subnet will be governed by a gateway, will go behind a gateway. So that is where you divide your collision zone. Okay, that is why we do subnetting. Again, if you did not understand it, I'll totally understand that, and we'll discuss about it later in the section, later during the discussion. Now coming to a few basic troubleshooting commands that you can use in your day-to-day life. For example, I have already shown you the ipconfig command. Ipconfig generally returns the IP configuration of your uh, machine, whatever IP address or gateway subnet mask is configured. Then you can use NSLOOKUP to see your DNS mapping. For example, google.com. I want to see what this FQDN translate to. So we talked about FQDN. What is FQDN? FQDN is fully qualified domain name. FQDN is a fully qualified domain name. So whenever you say google.com, that's a fully qualified domain name. That what does that mean is this is your TLD. Sorry, yeah, this is your TLD. This is your subdomain. Okay, no, sorry. This is your domain. The dot behind it is your TLD. This is your domain, and this is your subdomain. So it is a commercial site, and its subdomain is Google. That is how a FQDN looks like. So NSLOOKUP is used to see the A record in your DNS server. What is an A record? A record basically, so in DNS servers, there can be two types of records. Primarily, two types of forward lookups. First is, what is forward lookup? Forward lookup is basically FQDN to IP, and reverse lookup is IP to FQDN. Okay. So there can be two types of forward lookup records in a DNS server. One is your A record, other is your 4A record. So what is your A record? A record is your IPv4 address corresponding to the FQDN. 4A record is your IPv6 address, because A and AAA, what is, can you repeat? I think is it a AAA or A record? Okay, yeah, it is 4A record. 4A record is hex. So since it is IPv6 is hex coded, and every segment contains just 4 characters, 4 characters, because hex goes from 0 to E. So 0 to E basically hexadecimal. If you guys do not know, hexadecimal is 0 to 16, 0 to 15. That is 16 base 16 number, and after 9 you start counting A, B, C, D, E. So it is 10, 11, 12, 13, 14, 15, F till F. So that is what your hexadecimal is. So your IPv6 address is, IPv6 address looks something like this. And in a DNS record, FQDN to FQDN to 4A record means the IPv6 address corresponding to this FQDN. 4A record is this, and A record is this in a typical DNS server. So that is your NSLOOKUP. With NSLOOKUP, you can do forward lookup. You can see what FQDN corresponds to an IP address. And then you have IP config. I've already told you. Then you have ping. Ping basically checks whether a machine is up in the network or not, uses ICMP protocol to function. Then traceart. Traceart, I particularly like the story about traceart. So what traceroute does is it traces, it gives you all the hops. So all the L3 devices which are in between your computer and the destination computer. So between me and the google.com's router, last L3 device, there are these many hops, there are these many L3 devices which are making the routing decision. So that is how traceroute functions. How traceroute functions is, it is a very uh, very interesting story. So your whatever packet you send, it has a TTL and time to live, basically time to live. So and every hop, basically an L3 device, once your packet goes from this hop to that hop, the TTL reduces by 1. So how traceRT functions is, it sends first packet with TTL 1. So whatever, as soon as it goes to one hop, it dies and hence gives you a response. Second packet carries a TTL2. So it will go here, and then die, and then give you a response. Similarly, so on and so forth, unless it reaches the final destination that you have put as address. So that is how traceroute functions. It basically keeps on increasing the TTL of a packet by one number, and that is how you get it. So really smart use of TTL over there. If you find it interesting, I found it interesting. So that is why I wanted to tell. So we talked about subnetting. VLAN is a concept of L2. So VLAN basically again is a method of grouping network resources. So you can attach VLAN tags on different ports, and accordingly the data will be traversing through those ports on which specific VLAN is assigned. So based on the VLAN tag which is there in the your packet or frame, the data will be allowed to traverse. Similarly, coming to SDN, SDN is basically software defined network. So what used to happen so far is any network device which is there, it used to have a control plane, then there is a data plane. So data plane is where your data is moving, control plane is where your decision is happening. Say your ARP table, your routing table, your MAC table. This is what takes the decision of how to route the packet or frames. So what SDN does is SDN segregates this control plane to a separate module, and all the devices that are left with now is data plane. So anytime you need to push a new configuration, from a single console, you can push all the configuration. So that is your software defined network. In the next slide. Okay. So whenever we talk about network security in network, we shall focus on defense and depth. What does that mean? Say you have a device, you have a edge router behind which there is a server. You need to protect it. So instead of putting a single firewall here, we can segment it. And that is where the concept of DMZ comes into picture. So this is your edge router. This is your internet, edge router. Everything lands here. And then you put a firewall here and then segregate that these are my web servers and this is my DMZ, demilitarized zone. That what does that mean is whatever communication which is happening from outside will land here and go here. There's no route for the packet to go from here or here. So anything which is traversing here to here, and nothing can traverse from here to your inside network, and then it is your corporate network. So that is the concept of DMZ. Basically, you segregate and do not put any route between between your corporate network and your web zone, and that is how you segregate. That is how you create a demilitarized zone. What is a bastion host? Bastion host basically is something in which all the unnecessary services are taken out. For example, a firewall. A firewall runs a custom operating system, maybe a BSD or something, a Linux distro based on BSD or something, in which all the other services which are not required for a firewall function are stripped off. So that is what your based-in host basically is. Based-in hosts are basically purpose-made solutions, purpose-made applications, and they do not have any additional services running so that they cannot be exploited unnecessarily. So DMZ ho gaya, based-in host ho gaya. Then there is your honeypot. Honeypot is basically to lure attackers. So it basically imitates your network, not necessarily your network. It imitates your network. For example, maybe your actual internet banking website, you take a similar URL and publish it on a honeypot. So you'll see what kind of attacks are somebody is targeting on your environment. So these are used for statistical purposes to understand what kind of an attack surface are you looking at in your environment. So we talked about defense in depth, segmentation, DMZ, bastion host, honeypot, and then zero trust. Zero trust basically, you shall not work on whitelists. So there's two options when you're writing down ACLs, which is access control lists, or any policies for that matter. Either you can whitelist or you can blacklist. In case of whitelist, what you do is everything is denied except for the things which are whitelisted. And in case of blacklist, everything is allowed unless it is in the blacklist. So only things which are in blacklist will be dropped, rest will be allowed. So what zero trust means is do not use a blacklist, use a whitelist, so that there is an explicit based on requirement, there are explicit policies only. So communication policies must be fine-tuned to just have whatever is needed in the environment, and no unnecessary policies must be there. We talked about NAT, network address translation. Similarly, there's port address translation, that is PAT. So I've told you about IP address. Then let's talk about ports. So ports are basically like gates. So in a single server, say it is having an IP address of 10.02. This is my web server. It can accept connection on port 80. That is your plain text HTTP. Then it can accept connection on 443, which is your HTTPS. Then you may also be running your DNS server on this. So it is running on UDP port 53. That is default port of this DNS. Then you may also be having SSH for management of server. So that is port 22. And all this is using just one IP. So whenever we communicate on network, we always communicate on IP address port combination. So that is how you can, so that is where the telnet utility comes in picture. For example, telnet google.com at port 443, just to check if Google is listening on port 443 or not. So I've gotten a blank page. That means Google is listening on port 443 from my public IP that I'm trying. Okay. Now coming out of telnet again, and let's try doing SSH, because SSH shall not be running, because with SSH you can manage the services. So see here, SSH is not opening. Okay. So that is what I wanted to show you guys. In the internet, wherever you start communication, it always happens on a IP port combination, and ports are where different services are bound to. Different services are listening to different ports on different ports. So this is how a typical architecture looks like in a IP network with different ports listening to different services. Now coming to firewalls, we have already talked about tunneling, I guess, so we'll skip it. Coming to firewalls basically are devices which filter your traffic based on the ACLs or say rules or policies. And generally there is a top-down approach followed in firewall. So if you have one rule on top, and if it matches the condition, then it will be allowed. And unless a matching condition is found, it will keep on checking sequentially for all the rules, all the possible rules which you have written in your firewall. So the simplest form of firewall is a packet filtering firewall. It is basically a L3 device which looks your header information, again header and payload, which makes decision based on the header information, sender and recipient address. It makes decision based on that. Stateful firewall, it is slightly advanced than a stateless packet filtering firewall. Stateful firewall, what it does is, say you have a TCP connection approaching, it will send a SYN request, then there'll be a SYN-ACK, then there'll be a SYN again. ACK again. So what stateful firewall remember is, it will remember that, okay, it is a TCP. So it will expect that there'll be a handshake like this, and hence maintain a state table. Unless all these three are done, it will not start blocking if an allow rule is already present for those source and destination in question. Now, application firewall, it operates on L7. This is the most comprehensive type of firewall, and it is again functions on specific applications. So most common application firewall that we see is a WAF, web application firewall, which, as the name suggests, looks up HTTP, HTTPS traffic, APIs, etc. So it understands the L7 protocols and hence can make decisions based on the policies written for up to. It can make decisions for up to all 7 layers of protocols. And with this, our network and communication security session is over. I hope I've been able to make you guys understand a little bit about it, because network is, I think, the most difficult part of of all domains, and it requires a little bit of hands-on in order to understand each and everything completely. And since I was trying to finish the session in time within, say, 1.5 hours, I was trying to keep it concise. So pardon my brevity this time around. So yeah, moving to the questions from this session. A company has made a significant configuration changes that would protect them from most open system, basically OSI layer 4 attacks. From which attacks are they still vulnerable? So they are talking about L4. What is L4? Your time starts now. You have 20 seconds. I'll give you 20 seconds for this. It is a good question. I'll open the chat window now and your time starts now. Okay, your time's up. Okay, there is a divide in here. Okay, so let's figure out what protocol are we dealing with here. Ping is ICMP. Okay, in what layer does ICMP function? If you go back to the previous slides. Okay, so your ICMP functions are layer 4 already. Okay. Just a second, guys. Okay, and since they have already protected it from layer 4 attacks, 4 is out of question. Just a second. Give me a second, guys. Company has made significant configuration changes that would protect them from OSI 4 attack. Which attacks are they still? Okay, cool. Coming to the first option. First option is SYN. SYN flood is basically SYN, as you can related to TCP. TCP is on L4. So they have already put protection for L4 and hence 1 is out of question, eliminated. What is Smurf attack? Smurf is based on ICMP. And what is your Fraggle attack? Fraggle attack is against, works on UDP. So UDP and TCP, you're both working on L4. So if only you know what protocols operate on what layer and corresponding attack vectors for those protocols, then you can simply answer this question. Whatever is left is based on ICMP only. So here's your ping and here's Smurf attack. A Smurf is also an ICMP based attack only. So the option which is correct is D, option D, 2 and 4. Moving on to the second question. Determining the geographic location of a client IP address in order to route it towards the most proximate topological source of web content is an example of what technology? And you have 10 seconds for this. Yeah, ICMP operates on L3, sorry. Okay, cool. Wow. Why is Z? What is Z? Your time's up. So yeah, most of the people have answered A. What is a CDN? CDN is a content delivery network. We have talked about it in the third session when we were talking about cloud. So it is a cache, basically cached content located at nearby geolocation from where your user is accessing the content. Now the third one, end-to-end encryption is used by the user and link encryption is used by the service provider. Which of the following correctly describes these technologies? So we have again talked about end-to-end encryption and link encryption in the previous session. Here and your time starts now. You can start answering your questions. 10 seconds are there with you. So what was there in end-to-end encryption is your payload is always encrypted and your header information is always unencrypted. In case of link encryption, your entire header and payload was encrypted, but at every hop, it needed to be decrypted and re-encrypted. Definitely. So whoever has answered it as D is correct, as I've explained here. In case of your end-to-end encryption, only the payload is encrypted and header is not encrypted, so that the payload may remain encrypted end-to-end. That is why the name end-to-end. And in order to enable routing, the header is not encrypted, so that the source and destination addresses are visible throughout the network devices. Okay, with this, I wish to conclude this session. I hope you enjoyed this session, and I hope it had been useful. Yeah, definitely. I can explain link encryption. Link encryption basically is your, in case of link encryption, what we do is this your device. These are your two devices. Here's your header. Here's your payload. You encrypt the entire thing, and then you send it from here to here. Now, since it doesn't know what destination address to send it to, because your header contains your source and destination address, etc. So it will decrypt it here. It will see the destination address, re-encrypt it, and forward it to the next hop towards your destination. So that is how link encryption operates.